Hello again, folks, in 114.
Today we're going to be covering section 7.4, which is the last section of chapter 7 that is relevant to us. Today is, let's see, Monday, March 8th. Looks like, yeah, I'm sorry. Monday, March 8th, so we're right on schedule. One more class and then we have spring break. The packet that I have for you today is a couple of slides here. This is a diagram. It isn't immediately imperative, but I thought I would take the time to explain the usages of these terms, right? Because we're going to be using something that basically looks like a fraction. Here again is a diagram. I'm sorry if I'm it's like a broken record at this point, but this is a model that I would have you use when you're converting between units, which is what section 7.4 is about anyway. What's in the rectangle here is when you just have to do one conversion, and this is just a suggestion. If you have several conversions, sometimes you have problems that may be more than one unit you're converting simultaneously. Right. What is relevant from this chapter are these two tables of conversion factors. And we'll do a couple of word problems, 3 actually. Right. So if you're following along, do print that out. And we'll get started here. Take a sip of water here. All right. Let's see. Now you are already aware, all right? The topic initiated already is systems of measurement in the United States. There's the main system we have, which is really the Imperial System, because we were a British colony at one point, of course, which is perhaps defiantly so. We use this word customary system instead. All right? But it is what it is. It's the Imperial System by another name. Feet, miles, inches, furlongs, which is a more obscure unit. Ounces, fluid ounces, things like that are from the Imperial System. And many of those units, if not the majority of them, are from ancient times. Remember that even England itself at one point was more or less a colony of the Roman Empire. So many of the units, at least by name, are borrowed from the much earlier system, right? And then there is the more practical system, which does exist in the United States. It's just not something that we use as an official sort of system, the metric system, the standard international metric system. All right. What is going to happen in section 7.4 is that we'll be converting largely in this system. We'll do conversions of this. But also we'll do conversions between these systems because it is possible. There's going to be, unfortunately, some kind of loss in translation because you may have to round, all right, but it is possible. Right. Another reason that the metric system is really the superior system is because it's based upon 10, so there is really no rounding. There is just moving a decimal point here and there. All right. Anyhow, in all instances, all right, the model that you want to use, or that I want to sell to you anyway, is the model that would be practical in a chemistry class. Right. If you can identify two things: what is given to you and what you want. That is a unit given and a unit desired. Then you can, if such a conversion factor exists already, multiply by the conversion factor that produces this result. All right, remember a conversion factor, which goes by a different name in this book. They call them unit fractions. The same difference. Will do this job, right? Via a process of cross cancellation, all right? It'll cancel the unit that you're given and leave you with the unit that you want. Should put a little equals here for that reason, right? And it isn't too difficult to set up. You have to decide basically what the unit is that matches what is given and put it down below, and then place the unit that you want above. All right. And there'll be a cross cancellation effect, and it'll leave you just with the unit. Why decide that up front? Because that will also help determine where you're going to put the actual numbers involved here, right? So decide where the units appropriately go. Again, for this purpose, you want to induce a cancellation effect, basically, all right? And that will decide where the actual numbers involved will sit, right? The beauty of this is that you can flip the whole house upside down if you have to, right? It doesn't have to stay in this orientation. If it is practical the other way, you could just switch the position of the numbers and no harm is done. This is why it's called a unit fraction, because in reality, what you're multiplying by is a value overall of 1. It's just sort of disguised, right? The value overall of your conversion factor, or what you might call a unit fraction instead, is really just 1. It's just disguised, right? So multiplying by 1 is not actually changing the value of something, the identity. It's just changing its appearance, you know, if it's in this disguised incarnation. Anyhow, that is the model, all right? That is basically what I keep referring to, I've been alluding to for a while, right, in this diagram. All right, we'll do several of these problems, and it will make more sense, hopefully, as we go onward. Okay. Excuse me, I need a sip of water. I have to loosen my tie, it's choking me. Alright, let me show you a diagram in relation, and then we'll continue. I misplaced it. What did I do with that? I gotta find it. Give me 1 second. Looks like I'm going to have to steal it from elsewhere. So let me turn on my projector, because that always takes a while to boot. And while that is happening, I will swipe the diagram that I've neglected to save from here. And you failed me. There you go. Okay. This isn't your page yet because I have to change something. Oh boy, where did I put that? I'm sorry, I don't know why I didn't think to save this. I thought I had. It might be in your page. Let me take a look at that. The diagram that I'm referring to, I want to make available to you, but I don't think I posted it yet. So I'm looking to make sure. Where is it? Nope. Oh, okay, here it is. It was arduous. Yeah. This is the diagram that I'm referring to. Let me adjust the lights here. 2 cups of coffee and I don't feel it yet. I thought that I should summarize these different concepts because they are remarkably similar, they are related, but for future reference. All right, let's start with this. The basic idea that we have of some number sitting on top of another number, most people would refer to as a fraction, right? And there's really no harm done in doing that. It just so happens that a fraction has to have slightly more specific conditions than that. All right. So here's what when you have a fraction, there really is no decimal point sitting at all in the top here, nor is there a decimal point sitting in the bottom here. All right. It is overall something that would in fact be equivalent to a decimal. Like for example, 1/2 is equal to 0.5 if you divide 1 by 2, but in this form, the way that this looks, right, there's no decimal here and here, right? So that would be a true fraction when you see something that looks like that. If you want to be a little bit more open, right, to the possibility of there being any kind of type of number sitting in the top and any type of number sitting in the bottom, it would be probably more appropriate to say ratio at that point, right? So this idea of a general number sitting on top of some other general number, refer to that as a ratio, right? Any 2 numbers paired together really can be a ratio, right? If you see it in English context, in a sentence that's written in English at least, right? The words that you should look out for are these. The first thing, I'm just calling it A and B, and the second thing is B, all right? It would be something, the word to, and then something else. Right, A is to B. If you remember analogies, maybe when you were preparing for your SATs, right, you may have heard of something like that. Symbolically, we use this symbol in the United States. We use the colon, all right, to mean a ratio. All right, you'll notice the similarity between this and the division sign. All right, in the United States, we have the tendency to not just use a colon when we refer to actual division. We put a line through the colon. All right. But these are really synonymous, right? The folks I want to say in overseas in Europe, they tend to use the colon when they're referring to division anyway, because they really are the same thing. It's like, but there are times when you actually bother to divide, and then there are times when you just simply park things next to each other and go, well, that's a relationship of this to that, right? Alternatively, in English, you'll see something like this. First thing out of the second thing, right? These are the telltale signs that you're dealing with a fraction-esque ratio of some sort, right? Anyhow, they don't involve units really, right? And if they do involve units, the units would be identical and the units would in fact cancel. So for example, if you're talking 2 inches to 3 inches, right? And then you wrote them in the style of a fraction, 2 inches sitting on top of 3 inches, when you have similar looking factors, even the abbreviations for words like inches or factors, right, they would in fact cancel and just leave you with the numbers relationship. Okay? If you're dealing with a specific type of ratio, right, perhaps you're dealing with a rate. Generally speaking, and this would be applicable to a physics class or a chemistry class, all right, or maybe business as well and economics, all right, but a science really, all right. you would see words like this, like per, or for, or in, or an, in English, right? I can't vouch for anything else, unfortunately, but that's the way you would, if you see these words in English, all right, and then there's something in front of it and something after it, you're probably dealing with a rate, right? And rates are, these are conversion factors. Think of a conversion factor as being a tool that translates what you are given into what you want instead. All right? So if you've ever seen miles per hour on a street sign, in math world, it would be miles on top, per would be this line, and hours would be underneath it. And in theory, that rate would translate a physical an amount of time into a physical distance. Right? As long as you're multiplying by, the same thing here, cross cancel. Anyhow, usually, right, the rates are two different units. They measure different physical concepts. Like, for example, miles is a measure of distance, right, a length, if you will. Whereas hours is not, all right, a physical distance. It's an amount of time. It's a totally different physical concept. In this subject, what we're dealing with right now, when we're converting between units, especially units between systems, the imperial system and the metric system, they will in fact be the same physical concept most of the time. Like if you could convert miles to kilometers or vice versa, they're both a measure of physical distance, but they're still different, all right? So I'm deviating a little bit from the definition that I wrote here, all right? If you have something referred to as a unit rate, right? They're two different units, but the numbers are actually divided, all right? And then whatever you get, you might get some kind of a decimal on top. As a result, that's the quotient, all right? And then you would put a 1 under it, right, to disguise it more or less like a fraction, or what we think of as a fraction, a number sitting on top of a number. When it comes to something like a unit price, right, there's a very strict criteria. They're different units, but the top number is referring to money, all right? So you can't, in a situation like that, put dollars on the bottom. You have to put dollars on top. Or if you're dealing with another currency, yen, euros. I tried to get rupees, but for whatever reason, it didn't print. All right, the symbol for rupees. Anyhow, just realize that price is referring to money, and money has to be on top if you're dealing with the unit price. Okay? Anyhow, this again is primarily what we're dealing with. Right? Conversion factors that convert two different units into one, from one into another. Right? The given into what you want. Right? And that is how you would strategically opt for one conversion factor versus another. Here again, to blow it up, and I'm again broken record. Right? This is the model of converting, right? The thing that you see on the bottom is the same idea, just taken to the nth degree, all right? An extreme case. I think the coffee's kicking in now, so I suddenly feel more alert. All right, whatever you are given, whatever number and unit you are given, I would put it on the far left, all right? Times, right? Something that matches the given unit down here, all right? And then leaves always above. The thing that you want has to be on top. Well, at least to start. There's maybe one instance where you're doing two things simultaneously that we can deviate from that. But to get rolling, all right, what you want, the unit you want, on top. Okay? The reason that you rig something like this is, again, there's a cancellation effect of the given unit, right? As long as there's one incarnation of the given unit above the line and one below the line. It is like dividing without really consciously thinking about it. It's very strategic. It's kind of fun, all right? I swear to you, all right? When you this is the task and you're basically comfortable with it, and you go, all right, I have these two units, I don't want to convert them into these other two units, you will strategically rig the machine, if you think about it that way, as this is being some kind of machine. Set all the controls first, and then strategically cross out the things that you need to cross out. It's very satisfying, believe it or not, all right? And then you're just left with a number times a number times a number times a number very often, all right? Which you make your calculator do, all right, just to expedite. Now, here again is the last thing before I give you an example. These are the conversion factors that are relevant to section 7.4. Thing of it is, they're not drawn the way that you might like them practically, right? They're written as, to equate one with the other. Here we have the U.S. customary units over here. I want to say strictly, right? The imperial units. 1 foot is 12 inches. Anyone born in the United States most likely knows that. When you have something that's given to you like this, 1 foot equals 12 inches, here's what I want you to do. Right? I want you to take this same information and perhaps counterintuitively write it in the style of a fraction. Right? That is, something goes on top and something goes on the bottom. Because it's going to be used as a conversion factor, something that you multiply by that converts, all right, you have the freedom of choice to put it as either 1 foot on top, and I'm going to use the abbreviation for foot as FT, and 12 inches underneath it, or that upside down, 12 inches above, 1 foot below. All right? That's the beauty of this concept, all right? You can, at will, and you're not violating any rules, all right? Flip the position of these two things if it works for whatever the problem is, all right? You have a lot of freedom. Now you might go, this sounds like baloney, that I could just do something willy-nilly, right? And I got kind of flustered last week, and I said, I don't think it's willy-nilly. I mean it, all right? We shouldn't be willy-nilly, but this is not. There is actually a logic behind this. Even though these things look different, right? Overall, the concept of them, either oriented this way or oriented this way, is the amount of 1, all right? It's just more or less disguised. When you multiply by 1, you're not changing the identity of anything. You may be changing its appearance, and its appearance only. Anyhow, the bottom line is that it's totally legal. You don't really need to worry about it. Okay? This other slew over here of conversion factors, right? You're going to do basically the same thing. All right, these are kind of a hodgepodge, and you have to dig through them a little bit. But here's a very practical one, right? If for whatever reason you wanted to convert inches to centimeters, right, or vice versa, here's the conversion factor. 1 inch is really approximately 2.54 centimeters. Now, what you could do, again, if you're going to write this as a conversion factor, is that you could use abbreviations first of all right? You put 1 inch as the abbreviation for inches, right? Over 2.54 cm, right? That's a conversion factor. Or this situation flipped upside down. So 2.54 centimeters over 1 inch, right? Incidentally, all right, not to go off on a tangent, but if you've ever purchased clothing from something that has been manufactured overseas, I would say some of the nicest clothes you can get, all right, believe it or not, I'll say through Amazon or something like that. And sort of like the locus of like fashion seems to me to be somewhat in Asia these days, all right? So, not that I'm, look at me, I'm not too fashionable, right? But a lot of times I'll buy, clothes through Amazon or online, and they come from there. Anyhow, I want to say, in, say, Japan or Korea, they're obviously using the metric system, all right? But they're selling items here, all right? So there's going to be maybe some loss in translation, all right? Because anything that would be cut as a fabric would be cut in that system of units and then translated into a garment here, which is why you may find that things are slightly ill-fitting, all right? Americans tend to be heftier people. I mean, we need to exercise more, right? I know I do. But that's part of the reason is the math involved, I suspect, right? What I'm getting at is that there's some kind of rounding that has to occur when you're converting between units, right? And when you're manufacturing something, that may make a garment slightly larger or slightly smaller, right? Okay. Anyhow, any of these things that you see more or less written horizontally, you could write them more or less vertically, like this, in the style of a fraction. It may seem like you're violating some kind of a rule, but you're really not. Right? These are for distances here. These are for areas. You notice that there's exponents of 2 here. Then there's an interesting one, an acre and a hectare. This is for volume. Notice teaspoon, tablespoons. Right? What that equates to is milliliters. All right, and then there are cubic feet and cubic yards and cubic meters. All right, and down here is their weights, really. Ounces, pounds, and tons are the imperial weight. All right, what they would equate to as a mass. Remember, weight and mass are not the same thing. It's just that weight is proportional to mass. The more mass something has, it's going to naturally have more weight. All right, but they're actually different concepts. Mass is how much matter something is made of, and weight is the force that is applied to that matter. Okay. All right. Now, let's do a couple of examples, and I think I should turn this off now. I'm going to take a sip of water because I'm dehydrated. Probably too much coffee. Let's start with this. Remember, the name of the game here is rigging to cross cancel. You're going to strategically rig that model to cross cancel units. What I mean by that, I mean literally things diagonal from one another, they're going to cancel. So, let us say that you had this as a question. 26 ounces, that's the Imperial customary system, is how many pounds, right? So this is basically a US unit to a US unit, all right? We're not converting to metric yet. What you want to do is, again, borrow from the model. I'm going to write this and then superimpose upon it what is given. Then you're going to strategically arrange a conversion factor. And that's going to spit out what you want, like a little machine. Okay, so what is given is 26 ounces. So in this void here, I'm going to write this, but I'm going to write it with the abbreviation. So 26 would be seated here, and the abbreviation for ounces is OZ. All right, that's no coincidence that the Wizard of Oz actually is, that's the person's name. The wizard's name is Oz, right? It comes from the word ounces. All right, now, what is the unit that you want? LB is the Latin abbreviation for pounds, libra pondo, all right? So I'm going to put that here, all right? We don't know what that is yet, but that's what we're looking for, pounds, all right? And now, how do we arrange the conversion factor? Because there is, in fact, a one-step conversion factor. You don't have to do multiple, especially for this early example here. But we do want to rig this to cross cancel. So if I want, basically, if I want ounces to go away, all right, I'm going to strategically write ounces down here. And then if I want pounds as an answer, an outcome, I'm going to put pounds up here. Now you may intuitively know, especially if you were born in the United States, exactly how many regular ounces equals to a pound. But if you don't, all right, remember, you have a diagram to help, all right? 1 pound is 16 ounces. Right here we have that defined, all right, spelled out in English, pounds. as opposed to Latin. All right, but so because we have taken the time to decide what unit has to go where, that will force our hand now when we're parking the numbers that are related. All right, so if it is 1 pound, then 1 goes up here. Is 16 ounces, then 16 goes down here. All right. This is kind of the fun of rigging the machine, setting all the controls first and then going through it. All right. Anyhow, strategically, if these were like fractions, and they basically are, remember you can always stick a 1 under here and it's totally legit. All right. This is the effect. These cancel. They're the same type of units, 1 above the line and 1 below the line. It is more or less dividing without consciously thinking about it. All right. So what does that leave you with? All right. You could do some simplification first, but let's say that you didn't for argument's sake. You'd have 26 times 1 on top, which means that 26 would be above the line here. All right. And you'd have a 1 times 16 here. It is this relationship of 26 to 16 that you're going to use your calculator in this case, right? We're not reinventing the wheel right now. So you would enter 26, sorry for the glare. See if I can get it just right. You can get 26 divided by 16, enter, and there's your decimal, 1.652, right? 625, sorry, it's backwards. All right. So this is equal to, this is the answer, 1.625, right, pounds. 26 ounces is 1.625 pounds. That is something that is just shy of 2 pounds, right? Let's see. Is that quite right? Yes. All right. Because 32 would be 2 pounds, right? This is 3/5, so not 3/5. That's 5/8, I wanted to say. So it's a little more than a half, right? 5 divided by 8, yeah. Okay. Okay. 1.625 pounds. All right. Now that we mentioned pounds, let me just make you aware of something. An unfortunate similarity between units. Just beware, right? In the Imperial System, right, there are 16 ounces that are equal to 1 pound. But then there is a similar sounding unit, right, which is fluid ounces. 8 fluid ounces, and you would have to write that word, is equal to 1 cup. Right? Fluid ounces is often abbreviated FLOZ, right? And a cup is just abbreviated C. All right. Now, it's funny. When I make coffee, just for the sake of visual aid, right, I use a percolator, right? And I'll tell you something. It doesn't say it on the glass. All right, but here's my percolator, right? The percolator has, these increments on the side here, right? I haven't measured it lately, but I can tell you that when you get coffee, it says a cup by their definition is 6 ounces. 6 fluid ounces rather than 8. They're not being dishonest really. I think the reason that they're using the number 6 rather than 8, which is the actual mathematical definition of fluid ounces to a cup, because they're factoring in, you're mixing milk and sugar. All right? So just realize that when you buy something, the coffee, right, they may define it, in a way that's not quite correct. All right? It should be 8 fluid ounces is exactly 1 cup. Anyhow, these are very similar units, right? But realize that this is for weight, and this is technically a volume. Okay, even a box of cereal is measured in the United States. It's written as so many fluid ounces. 28 fluid ounces is like how much Raisin Bran you get in a box, I think. Yeah. Which is not that much. Yeah. Okay. Let's do some more. Let me show you the first word problem that I have printed from the packet. The one that looks like this, because I thought it was interesting. This is not technically converting between U.S. customary to U.S. customary, but it's still the idea of converting from one sort of a unit to another. It would still work. It's this particular first word problem I want to look at. I'm going to blow it up now with my projector, and then I'll sort of draw on top of it. Okay, I'm sorry. Good morning. All right, we're still going to do the same thing. We're going to try to rig up a little machine to cross-cancel units, what is given, to convert to what we want. Now, as a technicality, all right, money is not really a unit of measurement, right? It is a measure. It's a unit of counting, if you will. All right, so stylistically, they might treat it different, right? I spelled it out here, all right? $1 US could be exchanged for 12.99 pesos, all right? All right, this is a conversion factor, at least on July 28, 2014. Exchange rates for money change every day, right? So if I'm going to translate this into a conversion factor, it would be this immediately. It would be $1 US over 12.99 pesos. Right? If it is a convenience, you can flip these the other way. So you can put 12.99 pesos, right, over $1 US. I'm being very careful not to use the dollar sign, because I want to say, as a matter of fact, a peso, I believe, uses the same symbol, right? That symbol, right? Because American dollars come from Spanish dollars, right? And so do Mexican pesos. So we have a common origin, right? Aside from a lot of cultural things, money is one of them, all right? Anyhow, we can convert this, all right? I'm going to write my little model here, given, all right? The appropriate conversion factor as it would be oriented, and then what we want. Let's read the question a little bit further. What is in purple here? What is 2,500 pesos in US dollars? It's basically asking, what is so many pesos in US dollars? That's the thing we want. I'm going to put dollars here. All right? So, I'll put US dollars question mark on this side. And the unit that we have, red, is patriotic, right? 12.99, no, I'll get to that. 2,500 is what's really given here. Pesos. All right. And now, if we want to cross-cancel pesos, where would it be appropriate to put pesos in the conversion factor? On the top or on the bottom? The thing that is canceling is always on the bottom. So I'd just start with by writing pesos. And then I'll put dollars here, even though they're really the same thing, just from different countries, all right? And now I'll put the appropriate units, right? If it is basically pesos is a denominator, essentially, the bottom figure, then 12.99 would be down here, and $1 would be up here. All right. This is rigged to cancel pesos, and then the math, the actual numbers involved, would be these. 2,500 times 1 is just 2,500 as the top figure. 1 times 12.99 is the bottom figure. And then you would take your calculator naturally and divide one by the other. So 2,500 divided by 12.99. I don't know if this is visible, but I'll try. All right, that would be how you enter it. And you see that it's 192 and change. Sorry for the reflection. Now, think about this for a moment. This is the figure that you see that the calculator calculates. I'll put it up here. 192.455, and then there's more decimals. If we're talking about money, how far does money stretch in terms of a decimal? It goes as far as the hundredths place, right? The hundredths place is there, right? That would be, if we're talking about United States dollars, the position of pennies, basically. All right? So I'm underlining this because I'm going to round to that intuitively. Based upon 5 sitting adjacent here, what would this change to? Approximately 192.46. All right. Now, as the last thing, I need the space, unfortunately, so I'm going to erase this. How would you abbreviate these things? All right. I can't vouch for pesos exactly. I want to say, again, they use the same dollar sign because we both come from the Spanish dollar. All right. Our unit of currency. When you're writing this figure, 192.46 approximately, I really should put squiggle equals here. Where do you put the dollar sign really? Right? If you could spell out US dollars here, that's totally cool. All right, but rather than have to do that, right, what you can do is use this symbol that we have for dollars, which looks like that weirdly, right? Not really sure what the origin of that is, why anyone decided that was the symbol. But anyhow, it would be appropriate to put this in the front, right? This goes in the front, right? Not behind it, right? I have seen online, right, in context when people text one another and they communicate, and that's understandable, it's just casual conversation. They will put a dollar sign after it. That's not right, all right? I know that that's a trivial thing, but there's a reason why this is here and not there, all right? This is not measured, right? Measurements have a unit that goes behind the number, right? Money is not measured, it's counted, all right? Every sign that I've ever seen in public for my entire life, all right, has made acknowledgement of that. When you go to the supermarket, you don't see the dollar sign after the number, all right? So don't do that, all right? Then this is not a measured unit, it's a counted unit. All right? All right? Measured units go after the number. Counted units go in front. Money goes in front, essentially. Right? What does it mean to be measured, and what's the difference between measuring and counting? In order to measure something, this is an extreme example, something that is measured involves a tool, like this T-square that I have here, right? It's a little ridiculous in terms of its size, all right? But there's increments on here. When something is measured, it's going to be inaccurate to a certain degree, all right? And putting the unit after the fact, a measured unit after the fact, is making note of that there's probably some kind of rounding that had to happen if you tried to measure, the length of something, all right? It's only as good as the precision of the tool, with how fine the increments are, all right? Something that is counted, on the other hand, does not require a tool in order to acknowledge how much of it is. Like, even if you had a half of a dollar, as long as it had the actual green United States Treasury seal on it, it's still technically a dollar, all right? Even if it's like torn, shredded, worn out, whatever it is, even if it's only 3/4 of the bill long, all right? As long as you have the green seal, says U.S. Treasury, and acknowledges that it's a dollar, it's still a dollar technically, all right? No one at the bank is going to go, let me get out a ruler and see how long your bill is, all right? So make that distinction. All right? Money is a counted unit. The symbol goes up in the front. Things that are measured, actually measured, the unit goes behind. It involved a tool. Okay? You know, there is a certain etiquette. I know that it's not really super important, but you know, like I said, for my whole life, I can vouch for this. Every sign that you've ever seen in public always puts the dollar sign where it appropriately is, which is why it confuses me. Like, why are people suddenly not doing that anymore when they communicate? Right? I think it's a confusion between what is counted and what is measured, frankly. All right. Let's do another one of these. Let us convert $60 miles per hour, use the abbreviation that you see on street signs, all right, to start with, into so many feet per second. Now, this is worthy of our time because we have to dissect it a little bit, right? On street signs, if you see a speed limit, right, in the United States we use these abbreviations, MPH, right? Just realize that what this translates to is this, miles per hour. So if it's 60 MPH, it's 60 miles per hour, naturally, right? But what is this, if you see this magic word in here, per, in both cases? It's a rate, all right? Which means that it's going to translate one physical type of unit into another, right? If I were going to take the whole kit and caboodle, all right, and rather than sort of write it out horizontally, write it in the style of a fraction, or really to more appropriately say a ratio, it would look like this. The 60 would be on top of the line, miles would be adjacent to it, and I'm going to spell it out to begin with. Per is this line, and then hours would be underneath it. Now, just to make it look like a complete fraction, I'm going to stick a 1 here because that's really what the number would have to be. All right. So what's asking in this question is to convert from not just 1 unit, right, but 2 units apparently. Because look what is going on over here. On this side, we want the number certainly, but we have to decide what that number is based upon these units instead of these units. So this converted to something that resembles a fraction would look like so. The number, whatever it turns out to be, would be on top. Feet would be adjacent. This is the line per, and then it would be 1 second down here. And in physics class, as far as the abbreviations are concerned, the abbreviation for a second is actually S. All right. Very often you see meters per second, and it's M/S. But just for the sake of clarity, I'm going to put sec, often, all right, because I know I can get away with that. The abbreviation for hours, I'm going to call it HR. Miles is MI, not to confuse it with meters, right? And feet is FT. All right. Anyhow, what's interesting about this problem and what makes it different from those that occurred beforehand is that you're going to be converting 2 units at the same time. Simultaneously. All right. Not a burp again. Okay. So, what are we going to do to accomplish this? I'm going to borrow from my model, but just a fair warning, and it isn't going to be harder, really. All right? It will be, because we're doing 2 things simultaneously, more than just 1 conversion factor. It may not be 1, 2, 3, 4 conversion factors, that's kind of extreme, but it might be 2 at the same time. At least if you want to get it done technically in 1 shot rather than in 2 steps. All right? So, let me write this here. All right? Given on the far end, and what we want over here on this opposite end, and equals next to it. And then because there are 2 units, at least 2 units involved here, All right? In fact, I may end up having to use 3. I'm going to start with one conversion factor, and then I'll try to leave some space for extras that are occurring in here. So maybe let me stretch this out of the way a little bit further. Right. I'm purposely leaving space because I know that it's going to be more than one step, but it might be 2 or 3. Right. Let us see what conversion factors we have to choose from. Now, to be honest, obviously, we're all using computers. You can Google search it, and if you do that, you don't even have to do the math involved. I don't want you to do that, though. If you're going to use Google at all, or a search engine of some sort, all right, just use it to find an appropriate conversion factor, the actual fraction, all right? Not just get it to do the calculation for you, because that circumvents the entire thought process, and then you're not learning anything, all right? Anyhow, here's what we have on the handout for right now. You can always build up the toolbox later if you need to. Let's see. It is more appropriate to look at this side here. We have, what relates to what we have here? We have 1 mile is 5,280 feet. This was one of those fun facts I remember having to memorize as a kid. So I'm going to start by writing the thing that we have given, and then we'll decide what in fact we're going to use. I'm jumping the gun a little bit. So here's 60. That's going to go here. Right? 60 miles per 1 hour. Immediately, I can convert from looking at the table that's provided, this one over here. I can convert miles to so many feet, right? Because that is in fact what I want. I want so many feet per second. Right? So I'm going to rig this conversion factor, this first one, to accomplish that, at least of the two, the top one. Miles, M-I, or M-I-L-S, and then feet up here. Feet up here. Right? What are the figures involved that are given to us? 1 mile is 5,280 feet, right? Now, before, again, I jump the gun any further, I could cross-cancel the units, but resist the temptation just yet. Because realize what this is only going to accomplish. It's just going to leave you with feet, but it's still going to leave you with hours, all right? And what do we actually want? We want seconds. Now, as a person who lives on Earth, never mind in the United States, all right, you certainly know how long an hour is, all right? So even without looking it up via a search engine or asking somebody else, all right, you could probably figure out what the conversion factor is that is necessary. I don't believe that there is anything too complicated given here because they probably made the assumption that you know. There are 2, actually, all right? There isn't a direct conversion factor, but there are 2. 1 hour is 60 minutes. And 1 minute is 60 seconds. All right. Again, you might already intuitively know 3,600, and if you do, cool. All right. But humor me for a moment. All right. In order to get rid of hours over here, there needs to be another little part of this machine. Something that I can convert hours to. If I don't know that in 1 hour it's 3,600 seconds, then what I'm going to use is the little bit of information that's given to me here. I'm going to convert to the next unit that is possible according to this, the direct conversion. I can convert hours, which I want to cancel, so I'm going to put it up here somewhat ironically. All right, this is why I say there is an instance of where top and bottom, when you're trying to decide where the units go, it deviates a little bit. It's because this already started on the bottom. All right, hours I can convert to minutes. That it still isn't quite cutting the mustard. It's not seconds per se, but I'm getting there, all right? So in 1 hour, there are 60 minutes. Now, to complete this thought, I would in fact need, yes, a third conversion factor. And that is the one that completes everything, that finishes with seconds on the bottom. If I want seconds to be on the bottom rather than just having 1 unit on the top here, then I would definitely need to have seconds here. And what I'm going to need to have on the top is going to be something that cancels minutes. So I'm going to put this here. In 1 minute, there are 60 seconds. Everybody knows, right? What I've taken the time to do here is I'm setting the controls on the machine. This is the fun part of it once you get comfortable with this thought process. It's a great thing. All right, and again, in a chemistry class, this is the kind of thing that you do all the time, you know? All right, so now we can have fun, all right? We get the satisfaction of crossing out stuff because we were careful, all right? This is down here, this is up here, miles cancels. We're left with feet, we're not canceling that. Hours is down below, hours is up above. These cancel, even though they're not adjacent immediately. This is all commutative because we're dealing with multiplication here. So legally speaking, you could totally get away with that, all right? Simultaneously, minutes is down here below the line, minutes is up here above the line, and you're left with the unit that you actually want and where you want it on the bottom. So the units are perfect. Now see what you end up with. You have 60 times 5280 times 1 times 1, all right? That technically would be the stuff that is on top. Now, just for the sake of clarity, let me erase a little bit here and show you what would end up in this space. Above the line would be the product of 60 times 5280, technically times 1 times 1. That's above the line. The ones are superfluous. You don't really need to write them, but that is technically there. Right? On the bottom, it would be 1 times 1, which is 1, times 60 times 60, which means that this would be 60 times 6, well, technically, in this order, it would be 1.1.60.60. And our unit is feet, and our unit underneath is seconds, which is also just abbreviated S. Now, you could do yourself a little favor and simplify what is immediately easy to get rid of. 1 times anything is not changing anything, so you could dismiss that above the line. Similar situation down below. 1 times anything is really not necessary. It just is part of this mechanical process here. At the same time, if you feel like it, all right, you can do a little simplification. You notice that I put little dots here between the factors? That's to acknowledge that this was all multiplication above the line and all multiplication below the line. If you want to, you could cross-cancel the numbers now, all right? And it would give you the same relationship as really just 5280 divided by 60, all right? That has the exact same relationship. So here's proof of that. 5280 divided by 60 is 88. If you didn't do that, if you didn't have the level of comfort that you had, you knew that you can get away with that. Let's just say that you did the whole thing. 60 times, this is 88. 60 times 5280 would give you this figure above the line. Huge, right? 1 times 1 is 1. 1 times 60 is 3600. Right? You would be dividing this by this essentially. And what do you get? You get the same answer, right? Eventually what will happen, I promise you, if you do enough of these types of problems, you start to eliminate whatever variables there may be, right? I mean that in a very literal context, variables, right? And figuratively too, actually, all right? Anyhow, just like we're strategically crossing out units here, above and below, it has to be, they can't be adjacent to each other, next to each other. They have to be one on one tier and one on the bottom tier, all right? You could naturally do the same thing with numbers, right? It's a very strategic way of multiplying, right? And taking advantage of what math legalese that you can, right? Things that are commutative, the order in which you multiply doesn't matter, all right? Anyhow, this is 88 feet per second, right? Is what apparently 60 miles per hour is. 88 feet per second. Okay. moving on. All right, now what we're going to do is convert between the imperial system and the metric system, vice versa, and vice versa. Green is being tenacious today. I'm going to get a sip of water because I'm dying here. Forgive me. Not the sound of a dentist drill, I assure you. The neighbor is renovating. So I got some kind of drills going on, if you can hear that. Whining noise. It's either that or it's my paddle steering pump, which has been giving me problems lately. Okay, so the objective for now is we're going to be converting more or less from the US customary system to the metric system, and vice versa. All right. So here's a couple of examples. Maybe I could fit these all on the same space. At least try to chop this up into a half here. All right. So if you had this to begin with, converting 3,530 pounds into so many kilograms. And then in a moment we'll do this. 400 feet into so many meters. And I'm spelling meters, forgive me, the American way, which is ER, because that's where I live. All right. As opposed to RE, which is probably the French spelling, right? Where it originates from. You really should pay homage to that. Right? Homage is my homage, right? Instead of homage. Alright? I like homage better, that sounds nicer. Anyhow, remember, here's our model. Right? We have something that is given to us, whatever it is that you identify as being given to you. Just spell it would be great. All right. Times a certain conversion factor is going to spit out what we want. And then hopefully maybe we can do the same thing in a moment, but we'll get to it, right? Given times the conversion factor, or 2, is equal to what we want in this instance. So what are we given in this case? We're given 353,000 pounds. And what we want is kilograms, which is appropriately abbreviated kg. All right. So it's just one conversion factor rather than 2 simultaneously. So the unit that I want to cancel is the one that is, going to cross cancel down from down here. All right. And what I want is the unit kg. There is, if you look, right, a conversion factor that directly relates these two. Just realize again, it's rounded, so it's never going to be, exact really. Because we're talking about measurements here. All right, where is it? did I lose it? Down at the bottom. Here we go. All right. There's actually two. I'm going to show you the other one in a moment. It isn't listed here. 1 pound is a little less than half of a kilogram. All right. So we're going to use that. All right. So 1 pound is 0.45 kilograms. This is direct multiplication in this case. All right. What occurs naturally is that we've rigged the machine to do this, basically, to cancel the units and leave us with the one that we want. And then it's a matter of 1 times 1, which is just superfluous. Again, you don't have to put that. And then the actual multiplication of 353,000 times 0.45, right? What that ends up being, right? If you multiply these figures, 353,000 divided by 0.45, all right, you get, times rather, I'm stupid, times 0.45, you end up with this. Sorry for the glare. 158,820, it looks like. 850, so I'm reading backwards. Right. So that's what would be here. Right? 158,850. Again, I live in the United States. I'm putting a comma here rather than a decimal point. Point would be there. kg. All right. Now, just as a side note, there's another conversion factor if you want. It isn't listed on this. I'm going to give it to you. All right. 1 kilogram, if you're looking at it from that perspective, is about equal to, I want to say, 2.2 pounds. All right. This isn't listed there, but that is in fact another conversion factor. This is from the perspective of 1 kilogram, right? Rather than what is given to us, which is this, right? From the perspective of 1 pound, that is equal to 0.45 kilograms. It's a half a kilogram, roughly. 1 pound is roughly a half a kilogram, right? So 1 kilogram, that's a whole kilogram, is roughly 2.2 pounds. All right, now if we do this one, we're going to have to use a different conversion factor naturally because we're converting units of length, right, as opposed to masses from weight. Right. So 400 feet is what is given, so I'm going to write that here. All right. If I want that to cancel, I'm going to put feet down here, and maybe I may or may not. All right. Convert feet to something else. All right. So let me look at what I have. All right. From the table first. Right. I don't think we have something given that directly relates one to the other. So this may be an instance of where you have a second conversion factor. If you look at this table, and I'm glancing at it right now, don't pay attention to anything that has squares in it. As you see here, there's areas, right? And then there's volumes down below. That's not relevant to us, all right? What we have here is 1 foot is given a conversion factor of 30 centimeters, right? And then we have this, a yard instead, right? A yard is 0.9 meters, right? We don't have something that converts directly from feet to meters. So you could Google search it, and I'm sure that you'll find one. But let's work with what we have. I'm going to end up having to use a second conversion factor. This is really the point of this mental exercise. How strategic can a person be? Right? Again, once they get comfortable with it, they don't even bat an eyelash. They go like, I can handle that. All right. The conversion factors that we have convert 1 foot to so many centimeters. All right. We want meters though. All right. How many centimeters? There are apparently 30 centimeters approximately in 1 foot. All right. Now, if I'm going to have to cancel out centimeters as well, in the second conversion factor, I'm going to put centimeters over here and then meters above the line to end with that, right? So what's the relationship of a meter to a centimeter, right? The metric system, remember, is based upon powers of 10, so it is intuitive to us, and that's why it's a better system. There's no rounding involved. 1 meter is exactly 100 centimeters. Alright, so here we have our little machine rigged to go. Feet strategically cancels here and here. Centimeters strategically cancels here and here. And now we just have the numbers to deal with. You could, if you want to, if you're just staring at these as if they were just numbers of 400 over 1, 30 over 1, 1 over 100, you could do some simplification first. That would be strategic as well. But arguably, if you didn't think to do that, it would be top times top times top. You write that here. Bottom times bottom times bottom, and you would write that here. That would leave you with basically this. 400 times 30 times 1, and then 1 times 1 times 100. All right, I'm putting these little multiplication dots here in place of x's because it makes it a little bit more concise. All right? Now remember, you could, once you have it rigged like so, take advantage of some tricks, right? Mental math tricks, right? If you see 2 zeros, 100 down here, that would cancel this. And you'd be left with the same relationship of 1 times 1 times 1, which again is superfluous. You don't really need to write that. This would be 1 as a denominator. And then it really is just 4 times 30, right? Because it's 4 times 30 times 1, which means that this is 120 meters. All right, overall. Or you could just type it into your calculator, same difference, same ratio, technically. Okay? After a while, you get comfortable with it, you don't even think about it. Let's do some more. Here's one that involves an area. No, this is a volume technically, I'm sorry. Let's see. We're going to convert 700 cubic yards into so many cubic meters. We'll look to see if we have an actual conversion factor that does it directly in one step, or we will finagle something. We can always do that. Right? Let me just straighten this one out. Here again is the model. All right? What is given to us, I just can't spell for this to save my life. All right, times a certain conversion factor, we'll spit out what we want. Sorry for the faintness of green. I'm kind of taking advantage right now because it makes it a little bit easier to superimpose. Right? So I'm sorry if I had not neglected to consider the reflection here. All right, hopefully this isn't too unbearable. I'll turn that on. All right, I think that might be okay. All right, I think we're good. So, it's my own body shadow now. What is given is 700 cubic yards would be sometimes it's just CUYD is what they would write as abbreviations, all right? But you could also just do what is intuitive, YD with a little 3 here, all right? Superscript, all right? If we look in our available conversion factors from the textbook, there might be one that directly relates cubic yards to cubic meters, which is what we actually want. This is, again, cubic meters, all right? Spelled the American way, T-E-R versus T-R-E. Right, and that is actually correct. I want to say this is French. Yeah. All right. Anyhow, do forget it's French. We're a little, stubborn here. Right? We're your child too. France. Let's see. If you look down towards the bottom, you see things that have exponent of 3 here. Right? We do have a cubic foot. Right? Conversion factor, and we do in fact have a cubic yard. That's handy. Is equal to looks like 0.76, yes, cubic meters. Great. So we can do this in one shot. All right. The conversion factor is this. We're looking to cancel cubic yards, so I'm going to put that strategically on the bottom first. I always start with the unit. All right, that will help you decide where the numbers actually go, and then cubic meters would be up here. All right. Apparently, 1 cubic yard is 0.76 cubic meters, right? So, This strategically cancels this. It's over 1 technically, which is again superfluous, you don't have to put it. 700 times 0.76 would be the outcome here. What you should get, I want to say, is 532, something like that. 532 cubic meters should be an answer. Let me just verify with the calculator, and then I want to show you something if you get a little intimidated. 700 times 0.76 is indeed 532. All right, now, let us say hypothetically, again, you could always Google search it. You can probably find an appropriate conversion factor if it doesn't in fact do the math for you, which I would avoid. Again, I don't want to dissuade you from using a search engine for some practical reason, but right, try not to circumvent the actual mental exercise because it defeats the purpose of the question then. All right. If you had to finagle something, all right, remember, hypothetically, if you had to figure out a conversion factor on your own, here's what you might infer, or you might reason to yourself. If we're talking about something that's a volume, we're talking about something that its most basic unit would be a cube, right? So here's a cube, right? A cubic yard would be 3 dimensions that are the same. A length, a width, and a height, right? And let's just say that we've decided that if it's 1 cubic yard, then it would be 1 unit, 1 yard this way, 1 yard this way, and 1 yard this way, right? What you have to remember is that as we're talking about something that is not just 1-dimensional, but 3-dimensional, that in theory, if we're gonna build a conversion factor from scratch, right, we'd have to start with the basic conversion. What is this by itself as so many meters? Right? A yard and a meter are remarkably similar. A meter is a little bit long. It's like 39 inches or something like that. All right, so let's see if we have something to work with here. Yeah, here we go. 1 yard is a little bit smaller than a meter, so it's 9/10 of a meter. Right? So we would have this. This 1 dimension this way, the length is 0.9 meters. And since it's cubic, all of the dimensions must be the same. So 0.9 meters this way and 0.9 meters this way. Right? If a volume is a length times a width times a height, then it's this times this times this, right? Which is 0.9 times 0.9 times 0.9, right? 1 times 1 times 1 is 1 yard cubed. But these are meters, meters, and meters. So what's 9 times 9 times 9? 27, right? No, pardon me, that's not quite correct. 9 times 3 would be 27. What's 9 times 9 times 9? 0.9 to the third. If you're using a calculator, it would look something like this. 0.9, the caret symbol, that's that button over here, and then you fit in the exponent 3, right? 0.729. 0.729 meters cubed. I don't want you to be alarmed, but notice something. Based upon the information that is given in this sheet, right here, about the relationship of 1 yard to 1 meter, which turns out to be 1 yard is just short of 1 meter, this is what 1 cubic yard would actually be. That is, again, based upon that piece of information. In the same sheet, this is the conversion factor that we're given. I'll put a little asterisk here because it's not the solution. 0.76 meters cubed. These are remarkably similar, right? 0.76 versus 0.729. What would account for them being different? One of these is rounded somehow. All right? If you rounded that one, it would be 0.73, right? Which is still not quite 0.76, right? Whoever made the table, all right, didn't make a mistake. It's just that they took the information, the basic foundational information about this to this, and rounded at some point. They borrowed the information from some of the resource, all right? So beware of that. When we're dealing with measurements, there's always going to be some kind of rounding, right? That would account for this slight difference between these two outcomes, okay? Anyhow, that's totally fine. If you had to contrive a conversion factor from scratch, that's what it would be, right? Thankfully, they gave us one. It's excusable, you know? Somebody somewhere rounded. 0.9 is probably not that correct. You know, it's probably imprecise, right? And therefore is going to consequently be not accurate, inaccurate. It's only rounded to the tenths place, right? All right, now let's say you had this one. See if I can get these two again on one board. We're on an hour 20. We're going to convert 648 meters squared into so many square feet. All right. And this other one, we're going to convert liters to gallons. 1900 liters. Again, I'm spelling it the American way only for the reason that I live here. Not to be contrarian, really. All right. Let us see. Maybe, again, without being too much of a nuisance here, this is the model I'm following. Given times a certain conversion factor equals what I want. Right? Given times a certain conversion factor, ideally it's one step. I don't know if it will be or not, but that will be what I want. Let us see if we have a conversion factor that converts from square meters to essentially square feet, so it would abbreviate FT2, right? At least available on this sheet. All right, let's look at things where we see where we have an exponent of 2. We have square feet here, and that is 1 square foot is 0.09, it looks like. I'm reading it backwards, square meters, so cool. All right, we have a direct conversion for one area to another area. All right, so the what is given is 648 meters squared, right? If I want to cross cancel meters squared, I'm going to have to put it down here. If feet squared is what I'm looking for, then feet squared would be up here. And apparently the relationship is this. 1 square foot is 0.09 square meters. All right. This is strategically rigged, again, to cross cancel these units. All right, this is technically over 1. So it will be top times top, you put that there. Bottom times bottom, you would write that there. Visually, this would be 648 times 1 over 0.09. The ones really are unnecessary, right? It's really this that you're dividing by this, right? What do you end up with? Just to double check, all right? 648, turn my calculator on, would be great. Divided by 0.09, you get 7,200, right? 7,200 feet squared is the outcome. Square feet, feet squared, same difference. All right. Now we're going to measure capacities here. Notice that they're not using the cubic meter. They're just using the standard unit for capacity. It's the same thing. All right. Liters. All right. If you look, right, in this again, this diagram, all right, this table rather, that 1900 liters, which I'm going to abbreviate the way I was taught, which was capital L, all right, we're going to cancel it by putting it down here. What's the unit that we want? Gallon is abbreviated GAL. Right? It turns out that 1 gallon is 3.8 liters, which kind of sounds familiar to me from car engines. All right? The 3.8 liter was an engine that General Motors used to make. All right? Anyhow, apparently the displacement was 1 gallon. All right? I never thought of it that way. This is another example of where the metric system exists in our life, all right, in the United States. It's very appalling to me that we have to always, you know, as a teacher, you have to constantly convince the people that you live around, like, hey, it's already here, pay attention, you know, all right? But this is the nature of being a teacher. You're constantly, the sky is falling, and people look at you like you're nuts, all right? Well, if you say things like that, I suppose. Anyhow, liters would cancel liters, all right? 1900 times 1 would go here, which is 1900. All right, 1 times 3.8 would go here. You're dividing 1900 by 3.8, right? And you would end up with this, 500 gallons is the equivalent. Now just beware, again, these are measurements. That decimal of 3.8 is probably rounded, so it's always going to be accurate within a margin of error, right? Which means it's never going to be perfect, right? Ever, right? Measurements seldom are. Ever. All right. Now the last 2 things are those word problems that I dropped. I'm going to go back to now. All right. Let us discuss these 2 word problems. All right, and then we'll finish. I'll turn the projector back on and hit the lights. There it is. Come on. There we go. All right. Let's take a look at the blueberries here. And hopefully there's a sufficient amount of space to illustrate. Okay. Looking at example 2. This is just an exercise in rephrasing something, which is another thing. It's another skill, all right? People, especially Americans, myself included, you start out going through school and you are told that this is a textbook, it's very important, and don't write on it, right? Because it's borrowed, right? You don't write on things that don't belong to you, all right? And it kind of intimidates you, a little kid. You'll be like, oh, well, I'm not allowed to change things. I say this. All right, if you bought a physical copy of something, you could write all over it. And you should get in the habit of doing that, because realize that textbooks are not all created equal. Sometimes the author was not particularly good at saying something concisely and clearly. Sometimes they have purposely obscured information. So as a student, and we will all be, if you're in the profession of teaching, we'll always be a student your whole life. All right, teach your own students that they shouldn't be afraid to rephrase something, at least if it's correct. It takes a lot of experience to really be sure, all right? But there are strategies for that, right? Sometimes things are not written clearly on purpose, so you have to make them better, right? Especially for the kids, all right? So here's what we have to start with. This isn't too complicated, but it says if blueberries cost €9 per kilogram, all right? What would they cost in US dollars per pound, right? This is another example. We're going to have to convert 2 units simultaneously, right? I may have to move this, unfortunately. So let me, I don't think I'm going to have a sufficient amount of space. I'm going to open up my bootleg paint here. And see if I can get a fairly large screen. Just say, okay, that's fine. And where's my other thing here? Put that there. Right. Blueberries. Blueberry. Haven't had that cereal in 800 years. Alright, that looks like it's fine to write. Okay. Again, we're talking about money in this case, so again, we're talking about something that's counted. We'll have to put the unit technically in the front of the numbers in this case, not to obsess. All right. Beware, again, monetary exchange rates change every day. Sound like a real wino when you say that. Change daily, but just beware, right? Because I'm going to give you the one that I Google searched, like 2 days ago. All right. As of March 6th, 2021, the relationship of euros to US dollars was this. 1 euro, I'm going to spell it out first, is equal to 1.19 US dollars. And I have to say US dollars again because technically pesos, I want to say, is just really dollars as well. All right? They use the same symbols, I'm fairly certain. All right? There's also Australian dollars, I believe, and Canadian dollars. Anyhow, this is our conversion factor, i.e. our unit fraction that the textbook refers to them as. All right? And this is what it was as of Saturday, it was like. All right? Let me write my model again, all right, of what is given times a certain conversion factor. And again, we're going to have to do, in this case, 2 units simultaneously, so we're probably going to have to use 2 conversion factors. And this is going to spit out what we want ideally. Okay. Again, I'm purposely putting 2 bubbles here for the conversion factors that would go here and here because I know it's asking dollars per pound and it's asking euros per kilogram. So those are each 2 different things. All right. So let's start with what is given in red. I'll just intuitively use this red marker. All right. This is another thing. If you have the time, and I know that as a teacher, you will not always have the time. When you're writing a word problem as an example to give your students, do play with the colors a little bit because it will emphasize the important information. That is another way of sort of brainwashing a student to go, oh, I should look here. All right, they need that. All right, 9 euros, 9.00 would be over, all right, 1 kilogram. Now, the symbol for euros kind of looks like this nunated sort of epsilon, but it has an extra bar like dollars do. And technically would be in front, right? So if I want to convert from euros to, eventually I'm going to put dollars in blue, all right? So many dollars per pound. I'm going to have to put euros down here in that conversion process to cross cancel, right? And if I want dollars on top, then in this case, the exchange rate would convert from dollars from euros, right? I could already fit in what I wrote in black here, all right? 1 euro, the 1 would have to go down here for the cancellation effect, right? And it technically would be there behind it, right? Which is why I intuitively am not taking my own advice, but I should, right? Dollars would have to be here technically. And euros would have to be again here, right? So 1 euro is $1.19, $1.19. All right. Simultaneously, there's this issue with kilograms here. Remember, kilograms is a measure of mass, and we're converting it to a unit of weight. They're proportionate, even though they're not the same thing. So we do have an applicable conversion factor. If I want kilograms to cancel, since it starts on the bottom, I'm going to have to put it above the line, right? And if pounds is what I want to end with down here rather than just above, all right, LB would be down there, right? Now, our table that we have from the packet, all right, does in fact give us a conversion factor, all right? I mentioned the other one before, and you could use it if you want to, but stick with what the book has used for right now, all right? Apparently, 1 pound is slightly less than half a kilogram. So 1 down here and 0.45 above the line, all right? Now again, just to emphasize, the fun of this really, all right, is that you're rigging a machine and you're setting all the controls before you turn it on, all right? So now, if you make sure that the cross cancellations work, then the numbers will be positioned in the correct orientation above and below, and it will spit out what we want. The machine is good to roll here, all right? Euros cancels euros, all right? Dollars is left over. Kilograms cancels kilograms. Pounds is left over, right? So what do we end up with? 1 times 1 times 1. So you'd have 1 pound, so per pound, right? The 1 is superfluous. And then it is 9 times 1.9, 1.19 times 0.45, right? Would be the outcome that you get behind the dollar sign technically. Because it's, again, counted, it's not measured, all right? There's no device for measuring the length of money, and that would be impractical if there was. All right, 1.19 times 0.45. You should get this. I hope it's not too dark in here. I think that's just terrible. 4.8192. It looks like from this perspective, not 195. All right, 4.8195. All right, decimal would be here. So, not quite $5 per pound, all right? We're gonna round it to the hundredths place, which is where the 1 is sitting, all right? How come? Because we only have a unit for our money that stops in the hundredths place, known as a penny, right? It's 1/100th of a dollar. So rounding to here, where I'm underlining based upon this 9 adjacent on the right, this would be approximately $4.82 per pound. Right. Okay. Or you could write it like that: 4.82 line and then 1 pound underneath it. Okay. Now let's talk about this other type. This type that involves drug doses here. Question 3. Let me see if I can manipulate this. It's stubborn, all right. There we go. And I will erase this gobbledygook here. Here's an example of, again, what is given to you might not be phrased really nicely, at least not clearly. It might be even done so on purpose, to be purposely obscure. All right, so an exercise in rephrasing, taking the essential and boiling it down to just that. So a drug dose is often administered according to a person's weight. All right, for example, 30 milligrams of whatever the drug is for every kilogram, which again is proportional to weight. All right, of a person. If someone weighs, notice that this is in the imperial unit, 136 pounds, what would their dosage be? All right, now let's take a couple of things here. We have what is written, emphasized in green, is the conversion factor, right? It's just not explicit. So here we'll rephrase some of this, right, immediately. Rather than have this verbally 30 milligrams per pound, right? Or for every is the same difference. It's a ratio, remember. For, per, in, and, these are words that imply a rate, right? You would have this, 30 for every 1 kilogram, right? It would be sort of the more mathy way of writing it rather than the English way of talking about it, all right? If it is practical for whatever reason, and I don't think it will be in this case, I've forgotten now, you could orient it like this, right? This would be converting from a unit that you want, a dosage. This is a dosage rate, right, rather than a conversion factor that is the standard conversion factor. All right, 30 milligrams of whatever pill you're taking, right, to how much the person's weight is. It's technically a mass. All right, now simultaneously, they're giving us this much information. So I'm going to squeak my little model in here. Give in conversion factor. We may end up needing 2 in this case, I believe. It's going to spit out what we want. I hope that this isn't too faint. So let me just look at the camera here. And it is kind of bad. Because my green is dying here. But that's the skeleton that we're going to flesh out unique to this problem. The conditions unique to this problem. This may be a dud. All right. Oh, I hate green. I like the color. It just never shows up. Right. Given to us is 136 pounds. So I'm going to put that here in my model, LB. And on the far end, we want to know what their dosage is. The dosage is still going to be basically this, right? Milligrams per kilogram. All right. If someone weighs that, what would their dosage be? I guess we can convert this to pounds as well. So let's do that. Pounds. What would it be? Instead of having something expressed as so many milligrams per kilogram, what would it be milligrams per pound, right? Well, if this is what we're starting with here, all right, we may have to do some funny business here. They would cancel at some point. Notice that this is technically above the line here. All right, whereas we would want it down here. So that's maybe why it's necessary to have a second conversion factor. All right, I'm going to sit this conversion factor of 30 milligrams to 1 kilogram in here to start with. All right, I'm going to plop this in here. 30 mg is to 1 kilogram. All right, that's going to ultimately decide, because this is not going to cancel. All right, how I rig a second conversion factor for that sake of A, getting rid of kilograms, and B, making sure that pounds ends up as a bottom unit, all right, rather than a top unit as it starts, all right? What is the relationship of pounds to kilograms? 1 pound, we know, according to the table, is slightly less than half of a kilogram. So I'm going to take this information borrowed from tables, all right, if not the internet, all right, and position it appropriately. In this instance, I have kilograms as a denominator, so I'm going to strategically put it up here to cancel. Pounds is what I want as a denominator, so I'm going to put it here as well. All right. And there's going to be a double cancellation, all right? Now, what is the actual numbers involved? Right, again, 1 pound is 0.45 kilograms. Now that the system is rigged, let's see what happens, all right? This is going to happen for sure. Kilograms is going to cancel. Technically, because of the way that it's positioned, this is going to cancel as well, which means that we're not going to need this as a bottom. It's going to be understood that this is what the dosage is going to be. It's unnecessary to have this because of the cancellation effect, all right? Now, it would be on the bottom 1 times 1 times 1, which would be 1. Also unnecessary to write it. And then it would be 136 times 30 times 0.45, right? That is really what the solution would be, right? So what do you end up with? 136 times 30 times 0.45, right? You end up with this, right? 1,836 milligrams. Right, dosage. If a person, essentially what this is saying, if this is what it is for 1 kilogram, and we're dealing with a person that is strangely, their measurement of their weight is 136 pounds instead of their mass, right, and it's 136, right, this is what it ends up being as a dosage, based upon their weight, Alright? If they weighed close to 1 pound, it would be closer to this actual figure of 30. But since they weigh what an adult tends to weigh, 136 pounds or greater, alright, then that would be their dosage instead, alright? 1836, 1,836. This conversion factor is necessary, even if it's, notice the cancellation effect here, because we would need ultimately to convert 136 pounds into some equivalent. Okay? And that's that. All right. We are finished. So let me turn the light on here. All right. And turn this off. Alright, that was section 7.4, the only thing you're responsible for today. And we're done with chapter 7. Alright, so cool. The way that I broke it up, I felt that this is not a difficult concept really. I think the hard part of it is maybe just realizing the power that you have, alright? Why does anyone do poorly in mathematics? It's that they're scared, really, alright? And as the teacher, you have to take that fear from them, all right, somehow. All right? Don't be a bully, all right? Anyhow, be a friend, right? At least theoretically, all right? So, intellectually. So, for homework, all right, do section 7.4 in my lab. And then you're basically right on task, right up to schedule. Okay, all right, thank you guys for sticking with me. I'll see you again on Wednesday. Be careful out there.